Okay, let's start. As I told you, we wanted to go through some of the past examinations. So this is the very last one, the one of September. And the first question, as you probably noticed, is always about the forecasting, usually either forecasting in general or linear forecasting. And here, for example, we have AR1 process, zero mean AR1 process. It says that phi is smaller than 1 in absolute value, which means that the process is stationary. Okay. So there is a mean, and the mean, of course, it's 0 because it's, of course, AR1 without any intercept. And of course, there is a variance, which actually I recall there below. So there you see that I recall the autocovariant function of this process. Of course, here you don't have the variance of zeta because it's said that it's a standard normal distribution, so the variance is 1. So that's the autocovariance function of the AR1. And the question is, compute the optimal linear predictor of like 5 steps ahead, and also its mean square error. And actually, everything is there. You just remember to recall the prediction formula, the linear prediction formula, which is like linear regression formula at the end of the day, and apply it to this case. So let's try to do this. Maybe, I mean, you can do. There is not a real blackboard here, but if some of you want to try to write it down here, I'm not sure that anybody of you wants to do that. But anyway, so try to do it yourself first. So the first thing, of course, that you need is the linear prediction formula. So this would, maybe I put some reference so you can. So this is the exam of 17th of September. Okay. So the first thing you need is the linear prediction formula, which, if you recall, is just this one. Well, we have actually two scalar cases. We have a scalar y and a scalar x. So in this case, it's not even a matrix formula. It's just a scalar formula. So we have the mean of y, which in this case is just a scalar, plus it's all scalar, so we can even transform this into the covariance between y and x divided by the variance of x times x minus its mean. Okay. This holds just because it's scalar. Of course, you may remember better this one, which is the one that I presented to you. Okay, but this is just the same thing in case of a scalar. Y and x. Y will be very often scalar, but sometimes, I mean, in problems, we will see in past problem, x can be also a vector. So anyway, so what's our y? Well, our y is it's yt plus 5, and our x is just yt, right? So let's just apply the formula. What's the mean of y? It's a zero mean autoregressive process, so it's 0. What's the covariance between yt plus 1 and yt? Well, it's the autocovariance at log 5. So, well, if you want, we can write it down this way first. And then, of course, divided by the variance of x, which in this case is just the variance of yt. Let's just represent it this way for the moment, and then we will substitute the numbers because we have the numbers, of course, or the symbols actually. And then we have yt minus its mean, but the mean is still 0, so This is just it, okay? So this is just the 5 steps ahead prediction of a AR5 process, AR1 process based on information up to time yt. So let's turn these two numbers in these two formulas into numbers. So this is just the log5 autocorrelation function, autocovariance function, which is just phi the power of 5 divided by 1 minus phi at the power of 2. And of course, gamma 0 is just the variance, and this is just 1 over 1 minus phi to the power of 2. So we just need to substitute these two numbers or formula, like representation, symbols, whatever. So we have that the prediction of yt plus 5 with information y5, it's not up to y5, it's the only information you have is y5, okay, which is in this case is all the information you need, because it's called Markovian process, or the one Markovian process. So all the information that you need is the last information, like a random walk. This is an AR1 process is similar to a random walk under that let's see, point of view. So now let's just substitute these formulas. So we have y5, phi at the power of 5 divided by y minus 5 at the power of 2 times, we have to invert this. So this is just 1 minus phi at the power of 2 divided by 1. And of course, there's yt here. This simplifies, so it's just 5 at the power of 5 times yt. So this is the very simple way to do prediction in an AR1 model. Actually, in an AR1 model, well, if the mean is 0, of course, if the mean is not 0, you have to add the mean and take it off there. You just take the AR1 coefficient and take the power of h, where h is your horizon. So it's actually very simple. The question was also asking the mean square error, but the mean square error is also a formula in the case of, I mean, you can find it in two ways. You can find it directly, or you can find it by remembering the formula. If you remember, the formula of the mean square error is just the variance of y minus the covariance of y with x multiplied by the inverse of the variance covariance matrix of the x times the covariance between x and y, okay? So if you remember this, you can just apply this formula. So the variance of y, we know it, it's 1 over 1 minus phi at the square, minus, and here we have kind of the same thing we did just here, times that. So we can just apply that. It comes up phi at the 5th power divided by sorry, there's well, let's write it down. I don't want to confuse you too much. So this would be phi at the 5th power divided by 1 minus phi squared. Then the inverse of so 1 minus phi at the 2nd power divided by 1. And then finally, again, phi at the 5th power divided by 1 minus phi squared. So this we already had from before. We just have this. And so we can like write, so it's, well, below we have 1 minus phi squared, and above we have 1 minus phi at 5th power. Okay, sorry, 10th power. Okay, because it's phi 5 times phi 5. And from here, for example, you clearly see, now we have 10 here. In general, we have 2h, where h is the horizon. If you make h go to infinite, you get the marginal variance. Of course, in a stationary process, the conditional variance, if you want to predict at a very far away point in the future, will just be the marginal variance. It's very natural, because if you want to predict like in the infinite future, it's like you have no information. So the best information you have is the mean, of course, and the mean square of the mean is just the variance. Okay. You see already from here. So, okay. Of course, you can simplify it if you want, but this is fine. Otherwise, you could compute this mean square error directly if you want to. Like if we have like yt minus, so the prediction would be, sorry, yt plus 5 minus its prediction is phi at the fifth power times t, and you have to say take the second power. This is the mean, by definition, the mean square error. This is what we want to predict, and this is our predictor. Okay. And let's just, I mean, here this is more complicated than remembering the formula, but of course we can write this yt plus 5 as increments with respect to yt. How do we do that? Well, if we apply the definition, actually we call it zeta, I think. So zeta 5. Then I substitute this also with its formulation, and so I get 5 times phi yt plus 3 plus zeta 4, and then plus zeta 5, which of course becomes equal to phi 2 t plus 3 plus phi zeta 4 plus zeta 5. And of course I can go on by substituting this with the previous, with its own definition. So this would be phi 2 times phi yt plus 2 plus zeta 3, and then we have plus phi zeta 4 plus zeta 5. It's much more cumbersome. Knowing the formula in this case helps you save some time. But we do that just, I mean, it's just an exercise. Why not? I mean, after this, you kind of see the pattern. So in general, we can go on, we can write, this is going to be 5 at the power of 5 times t plus, and then we have just the, we can order the other way. So zeta 5 plus phi zeta, sorry, this is a 5, phi zeta 4 plus the square of phi zeta 3 plus phi zeta 2 plus zeta 1. So this is basically, sorry, here something is missing. No, I'm doing the opposite. So 3 and 4. 1, 2, 3, 4, 5. Zeta 5, which is the last one. Okay. Sorry, it actually was t plus, oh, sorry, I made a little mess. It should have been t plus 5 here. Okay. Okay. So there are all the t missing from. And so we should have 5, 4, so t plus 5, t plus 4, t plus 3, t plus 2, until t plus 1, of course. So this is just a different way to write the observation of time t plus 5 as a function of the last value known, which is yt, and then all the innovation that they're kind of accumulated, also multiplied by some numbers. I mean, if you go back to the random walk, if you remember how the random walk, if you put 5 equal to 1, then this 5 kind of disappears and you obtain exactly the results that we obtained from the random walk. But anyway, so this is the let's say the easy way to proceed. So now we have an expression of this as a function of information up to time t plus some random shocks, which they all have mean 0, of course. But we're interested in the variance of this object, so because we have to take the square. So we want to compute this, which is t plus y, which is now which we now can write this way. Maybe this is shorter, or 0 up to 4. Okay, square minus the prediction, which was just this one. Okay, sorry. Okay, so this is the real observation, which we wrote down in this way just because we wanted to represent it as yt and sum of innovations, and this is our prediction. Okay, so this of course goes away, and what remains is just the variance of this like linear combination of white noise. Okay, and yeah, which is of course well, all of these have variance 1, so this is just well, just the square of it just would be so the first we will have the variance of zeta, but then the variance of zeta is just 1. You have to think we have to take the square and also all the cross product, but of course the cross product in the expectation they are 0 because zeta is a white noise. So the only thing that survives are the squared terms of this squared, and so we have 1 plus, then would be the first 5, but then there's the square, and then there's phi 3, but then there is the square, and so on up to phi 8. Okay, and that's it. That's just another way of writing this number. Okay, now if you go back to the rules of the series of, then you get the same. You get the same number. Is that right? T più 5. Aspetta, sì, no, c'è un più 1 qua. Sì, perché c'è una differenza sempre. Sì, diciamo che questo esponente e questo devono sommare sempre a 5. Hai ragione. Quindi, sì, esatto. Quindi quando questo è 0, sì, c'è un più 1 qua. Hai ragione. Comunque questo non, diciamo, non cambia il risultato. Comunque hai ragione, grazie. Anche qua. Okay. But I mean, if you just remember these two, as I told you at the beginning of the course, there are a couple of formula that you should always take with you, and this pair here you should always take with you. I mean, if you're a statistician, you should already have that into your tool. It's very simple. It's just a linear regression formula at the end of the day. Okay. Or if you want to see a more in a more mathematical way, this is just like a linear projection into in a Hilbert space. Now, let's go on with the next question. Well, this is just like yeah, connecting things. So I'm asking you, so I'm giving you 4 processes. So AR4 seasonal MA1 with the seasonal frequency equal to 4, a seasonal AR1 with seasonal frequency equal to 4, and the MA4. And I'm asking you to unite or to give the right name to the right autocorrelation function, okay? So, some idea? Posso scrivere su sto coso? Dovrei. No, questa è la firma. Boh. Non mi fa scrivere liberamente. Adobe è un po' una ciofeca, devo dire. Da questo punto di vista. Vabbè. Beh, posso disegnare. So, any idea? So, which one of these is the AR4 process? These are just autocorrelation function. There is no partial, okay? Or which one of these is the MA4 process? Il primo cos'è? Sì, questo qua. Porca, questo qua è sbagliato. No, qua c'è un errore. Ups. Lasciamo perdere il primo un attimo. Lasciamo perdere il primo. Allora, facciamo una cosa inversa. Questo qui cos'è secondo voi? È il secondo, questo qua. AR1 stagionale, ok, giusto. Facciamo seasonal AR1. Poi no, vabbè, in realtà è giusto, scusate, non ho sbagliato. Mi ero già terrorizzato di aver dato un esame sbagliato. Poi questo? No, in realtà questo è un MA1 stagionale perché no, nel M1 stagionale avete solamente fuori la prima autocorrelazione stagionale, poi basta. Ok, andiamo a questi, scusa, avevo letto male. Ricordate che la R4 può avere coefficienti da 1 a 4, non deve avere per forza il coefficiente uguale a 4. Ok, quindi questo, giusto. E quindi questo. Perché questo? R4 comunque va giù gradualmente, poi in questo caso addirittura mostra queste, diciamo, queste sorte di movimenti stagionali, perché di fatto mostra quasi. Quindi va giù, comunque l'idea è che questo vada giù gradualmente, ok? Mentre l'MA dopo 4 è sempre uguale a 0, infatti succede, da 5 in poi, no, vedete, è sempre 0. Stessa cosa qui, ma a livello stagionale, l'MA è diverso da, in questo caso, il primo ritardo stagionale è l'unico diverso da 0, e qua invece sui ritardi stagionali la R va a 0. Okay? So let's go back to English. But this is the right answer. Okay? Okay, this is like this is just a question about the two typical forms of seasonality that we use in unobserved component models. And of course, if you, it's just to be very synthetic, but usually we have like the stochastic dummy one, which is just this process, or let's suppose that this is the seasonal frequency. Okay. So the dummy one, stochastic dummy one, okay, you can write it this way. Of course, you can also say, okay, I can put this in state space form. I mean, this could be already the answer, but if you want to be a little bit more complete, you can give me the var1 formula of this, which would be T0. Plus 2 actually. Then we have all minus 1, and here we have like actually this way, sorry. And here we have just the delay of the same thing. You can write it, I mean, I'm writing this like in a very of course, this is already giving a meaning to the vectors. Of course, this would be all right. You don't have to fill this up if you want to. Okay, this is just the autocovariance function. Of course, you can also say, okay, the zeta one, just take the first one and then put all the other to 0. So this is one way. As I told you, you can be very schematic. You don't have to write a lot. This is already true. I mean, if you write this even better. The other one is the trigonometric, stochastic trigonometric, or which is just, let's define, for example, the seasonal frequencies. Then this is just the sum. So the seasonality would be just the sum of this gamma j objects, so s divided by 2 integer parts of these objects, and these objects are just defined this way. So this is just the rotation matrix, and we have, of course, the same thing here. And these are white noise. Well, you can write with variance covariance matrix equal to this. Okay. Basically, that's it.
So the dimension of the stochastic dummy vector is s minus 1.
The dimension is s minus 1. And that's what I defined, right? Yes, it's always as, remember, it's always s minus 1. Whatever representation you prefer, it's s minus 1 vector. So you, of course, you see, I also I always have to think about the indexes. I know that, and so I have to turn things out so that the indexes are the right one. And I think I did it right here. So the dimension is always s minus 1. Of course, here is s minus 1 because if you remember, if s is odd, we have exactly s minus 1 values. But if s is even, then the last component, so the sign component, disappears. So we have to throw that away. We still have s minus 1. Okay. You can write down if you have time, if you remember. Of course, everything about this you add is something more, but I would satisfy it even with just the simplest answer. So, okay. Then let's go on with the fourth question, which is so this is, for example, very often a question when I ask you to put some arbitrary model in state space form, usually simple models, but it's about you being able to build a state space form for a given model. So this is a random walk plus drift. And then there is a regressor, just one, with a regression coefficient that evolves as a random walk. And then, of course, plus white noise. So first of all, how would you... So how would you need to have this part here? Well, you need two state variables, of course. Boh, vediamo se si funziona anche qua. È un po' meno sensibile dell'altro. So here we would have like mu t. No, okay, I'll use the other one. So this is question 4. So first of all, let's go with the random walk with drift. Well, in order to have the drift, you need the drift. You need the slope or whatever. The slope is the drift, okay? And then, of course, we will have other things here. So let's start with the top part. And here it's just like a local linear trend, okay? But if we want the drift, so the random walk with the drift, so the drift doesn't evolve in time. So here we have 0, and here we have usually we call it eta. Okay. So there is a drift. So the slope is the drift, but the drift doesn't evolve in time. Okay. And this is the first part. And then we have, and of course we can always start writing also the other equation. So we keep the mu and we throw away the beta because the beta is just a construction, the state variable, okay? And of course there is the white noise, so let's just leave it there. Then, of course, you know, we have just to diagonally stack or concatenate, whatever you want to call it, all the components. So the next one will be if it's just a regression whose coefficient evolves as a random walk. So remember that when you have regression, what goes into this state vector is just the regression coefficients, right? So here we just have one more state variable, which is delta. And here's delta. Sorry, here's delta. Okay. This is just a random walk, so it's 1, and all the rest, of course, is 0. 2 zeros. Okay. And of course, this is random walk. It will have some noise. We can call it zeta if you want, whatever. This is a white noise. These are all white noise. So this is the white noise vector. And here we just have the regressor multiplied by its coefficient. And that's it. Of course, you should always give me the initial condition. What about the initial condition? Well, they're all non-stationary state variables because it's a random walk plus drift. The drift is just a constant, but a constant in a non-constant. I mean, if you have to think about the initial value, if you know nothing about the constant, you give a diffuse initial condition because knowing nothing implies. So if you complete the state space form, you have to say, okay, the expectation of alpha 1 would be, well, arbitrary. Usually it's put to 0, but the variance covariance matrix would be diffuse. Okay, and here we have zeros. Because the first the first is a non-stationary component. The second one is a constant component, but unknown, completely unknown, unless I know some information. And the third one again is random walk, which is non-stationary, and so you put an infinite variance. And these numbers are really arbitrary, okay? Because they really don't count. So if you have an infinite variance, whatever number you put is the same. It doesn't really matter. Okay. We could cut a bit. Okay. And this is also white noise. Okay, last question of this exam was oh, okay, this is more like qualitative. I'm not asking any particular formula. So how can you find out using UCM in state space form if there are additive outliers and level shift? If you remember, I told you there are the so-called auxiliary residuals. So this is question 5. So we can use, of course, the auxiliary residuals. And what are the auxiliary residuals? Well, if we call eta t the vector of state disturbances, so the white noise not driving the states, and epsilon t the observation noise, then we have the so-called disturbance motor. Okay, so the disturbance motor, if you remember, is just well, let's put it as a linear problem. So the linear prediction of this vector on all the data. So if we can call all the data this kind of calligraphic n, and the same holds for the disturbance motor of the observation noise. Okay, so what are the auxiliary residual? Well, the auxiliary residual are just the standardized version of this. So auxiliary residual are standardized means just divided by the standard deviation, because of course they are zero mean processes, okay? And of course, if they're particularly large in absolute value, it means that in this, okay, so the question is asking additive outliers. Of course, for additive outliers, you have to look at the auxiliary residual of the observation noise. So if there are extreme values in the auxiliary residual of the epsilon, then you find outliers. You think, and of course, then you can model them with dummy variable. And of course, you have many of these. Usually, you have the ones of the level, the ones of the slope, the ones of the seasonality state variables. But if you take the auxiliary residual of the level, or actually of the level's disturbance, then if you find an extreme value, it means that there is a extreme change, an abrupt change in the level of the time series. So here you find the level shift. So this is level shift. And remember that you find it one period ahead of what's actually happening in the data. So if you find tau to be a time where there is time with extreme auxiliary residual of level, let's just call it of the level, of the level equation. This implies that at tau plus 1, there is a level shift in the time series, okay? That's basically the exam of September. Is everything clear, or something that I should review? So from the first